All right, everyone. 12:50, right on the dot. Good afternoon. I hope you all had a wonderful weekend. As I said about 5 minutes ago, after class, I did bring back problem set number 1. It's in the back here in alphabetical order. If you want to pick that up, that would be wonderful. Don't forget that on Wednesday, problem set number 2, part 1 and part 2 are both due on Wednesday. And we're going to be going over the chord conductance equation today. That's probably one of the only things that you may not be able to do on problem set number 2, part 2 yet. So we will be going over that today. And if you have any questions, I can hang out after class, right? We can go through some of the problems you might, not be too confident about. If you want to write this down, these are the 4 equations for this section that I want you to know. There's 4 things, okay? And it pertains to problem set number 2. Number 1, you're going to need to know how to calculate the equilibrium potential, okay? So if this still is a little bit fuzzy for you, or you're not real confident with it, take some time and practice, right? Yes, question? Great question. That will be stapled to the back of your exam. You do not need to memorize that equation, okay? In fact, if you actually look at the tab on your Canvas website where it says for review for exam 1, you'll see the actual equation sheet that will be given to you during exam 1, okay? So you don't need to memorize any of those equations, okay? All right. Great question. So 4 things that you need to know. Number 1, you need to know how to calculate equilibrium potential. Number 2, you need to know which way the ions are moving. And that takes a little practice. If you've not quite mastered it yet, that's okay. But it is something that you need to work on, okay? We can talk about it again. There is a slide that actually gives you some text as to how to determine which way an ion is moving. All right, that's number 2. Number 3, you need to calculate driving force. And we're going to talk about that today. How do you calculate driving force? When we talk about Ohm's law today, we're going to go through driving force and what that is. Simply, it's a simple subtraction. It is the membrane voltage minus the equilibrium potential. That is the driving force. Very simple calculation. Now that won't be on your exam. You do need to memorize driving force equals Vm, membrane voltage, minus equilibrium potential. And we'll go through this today. And then finally, you need to predict what the actual membrane voltage is going to be. You can do that using the chord conductance equation. And that's what we're going to finish up with today. So we're going to run a calculation. You'll be able to predict what the resting membrane potential is just by knowing something about their equilibrium potentials. All right? Don't worry. We're going to go through that all today. So now, after today, you should be able to complete problem set number 2, part 1 and 2 pretty easily. All right? Okay, so again, as always, we got a top hat question here. If you don't mind getting your top hat devices out. Just got a couple today, but it pertains to what we've been talking about. Now, again, you should have in your mind, you should master what exactly is the equilibrium potential. We talked about that last Friday, pretty much in a lot of detail. So today, true or false, at equilibrium, the electrical and chemical work expressions are equal in magnitude but opposite in direction. Is this statement true or false? And you can turn to your neighbor. This is basically the definition of electrochemical equilibrium. Electrochemical equilibrium.
How was your weekend? Good.
I thought you might have left already. So.
Oh, no, it's okay. I'm sorry. No, it's okay.
So I answered that text late,
No
so
worries.
sorry. And
It's
I was
all
like, oh, not sure. All right, we're already up to 82 students, 83, so I'll give you about 10 more seconds. All right, anyone in this room need a little more time? I will be getting those top hat points in today. You'll notice that your problem set number 1 has been graded and is entered. All right, so go ahead and close this, and this is actually a true statement. All right, good job. 98% of you got that right. So when you've reached the electrochemical equilibrium, that means that the electrical and chemical work are equal in magnitude but opposite in direction. That is absolutely true. All right, one more. If the measured membrane voltage or the resting membrane potential, if the cell is at rest, then the membrane voltage is the resting membrane potential. If that measured value is equal to the calculated equilibrium potential for potassium, which statement is correct? A, net movement of potassium will occur down its concentration gradient. B, there will be no net movement of potassium. C, net movement of potassium will occur against its concentration gradient. Again, you can talk to your neighbors. Just want to make sure that everybody understands these concepts. And again, right before the exam, I will open up all of the top hat questions for review with their answers.
I'm still stuck on that.
Okay, let's talk. All right, we already have 88 students that have answered. Give you about 10 more seconds. Anyone in this room need a little more time? Raise your hand high if you need a few more seconds here. All right, here around this column. Okay, so go ahead and close this, and the correct response is B, right? Nice job. All right, if the actual membrane voltage that you measure with a voltmeter is the equilibrium potential, they're sitting right on top of each other, then you're at electrochemical equilibrium, and there's no net movement of potassium, okay? So, great job. 93% of you got that right. If you are confused by these topics, by these concepts, please come talk to me. You can come after class, or you can come to my office hours today and tomorrow. Make an appointment or just come during the office hours. Any questions so far? So my point here with these top hat questions is by now you should master what equilibrium potentials mean, okay? What they mean. And with that, you can predict which way ions are moving. So let's go ahead and move on. Today we're going to be talking about Ohm's law and the resting membrane potential. Okay? Oh, please. Okay. Let's see here. All right, so we're going to start off with Ohm's law. We've talked about Ohm's law before. Here is our roadmap, if you will. Last Friday, we learned about diffusion of charged solutes and the concept of electrochemical equilibrium and how to calculate the equilibrium potential. Now, today we're going to talk about the definition of current, voltage, and resistance, and conductance. We should add that. It's just the inverse of resistance. That is Ohm's law. So when we talk about current, voltage, resistance, and conductance, we are talking about Ohm's law. Then we're going to go into the resting membrane potential, revisit Bernstein's hypothesis. How do you really think about the resting membrane potential, and how can you predict it using the chord conductance equation? And then we'll talk about the contribution of conductance and driving force to the resting membrane potential. So these are, like I said, I always try to put the learning objectives up front. These are really easy. Understand Ohm's law. Know the definitions for current, which is a flow, voltage, which is your driving force, resistance, and conductance. Okay, that's all kind of rolled into Ohm's law. Now remember garden hose physiology? We've talked about this before. The water that flows through the hose, it's actually going to move because of a driving force. That driving force is going to be the pressure gradient, because water is always going to flow from high pressure to low pressure. That's going to be the net flow. Okay? So the driving force is the pressure gradient. The net flow will be from high to low concentration, or low pressure. Flow is actually, you can think about it like a river of water molecules, right? Flow is going to be in mils per second or mils per minute. That's, in this case, with electrical terms, we're going to be talking about current, which is a river of charge. It's charge per second, which is an amp. Okay? Then we'll talk about resistance. Resistance in this analogy is if you kink that hose, you're going to disrupt the flow downstream. And conductance, which is the inverse of resistance. So with that, here is a very important slide. With this slide, like I said before, terminology is really important. Okay? So knowing something about these terms, that's going to be really important. All right? And let's just take it from the top. Go to the title at the very top of the slide. Ohm's law is key. It's central to many different fundamental concepts in physiology. And it's equal to the driving force. For electrical terms, again, that's Vm minus Es, the membrane voltage minus the equilibrium potential of a particular solute. Driving force is equal to flow times resistance. In electrical terms, the flow is actually current and resistance times resistance. Ohm's law is key. So I want to start off with that. Now we're going to define all of the different components. We're going to start off with I, or flow. And like I said before, current is usually depicted as a capital I, is the net flow of charge. So you can think about those ions. Each one of them has, one or two charges associated with it. And as they move about, that flow of charge is going to be the current. So 1 ampere, is equal to 1 coulomb per second. A coulomb is a unit of charge. Okay, so coulomb is the amount of charge on a mole of any monovalent ion. A monovalent is an ion that has only one charge. Divalents have two charges, like calcium and magnesium. It's a unit of charge, okay? Okay, so I think about it as a river of charge, right? A river of positive or negative ions moving about. Okay, so let's move on. What is the membrane voltage? And I think what's really important here is to kind of define membrane voltage. There's a lot of different names for this. Membrane voltage can be Vm, right? This is membrane voltage. It's the exact same thing as membrane potential, right? We could also say membrane potential. It's the same thing as potential difference across the membrane. Remember that inner leaflet is basically reference to the bath, which is 0. Or when the cell is at rest, we call this the resting membrane potential, or RMP. See how these are really all the same terms? I use them synonymously. A lot of people use these synonymously, and I just want to make sure that everybody understands that we're talking about the same thing. Okay. Any questions about this so far? All right, so if we go back to our slide here, the membrane voltage or potential difference is measured in volts, and it's the work needed to move a unit test charge in a frictionless manner from one point to another. 1 volt equals 1 joule per coulomb. So when we actually ran the numbers with the Nernst equation, remember we got joules per coulomb? That was a volt, and then we actually had to convert that to millivolts, right? 1 joule is the amount of work required to move a coulomb of charge across a 1 volt potential difference. So this is the net driving force. And this is what you'll need to know in your mind to calculate the net driving force when you come across the questions on your problem set and questions on the exam. Again, the questions on the exam are going to be almost identical to the questions in your problem set. So make sure you've mastered that problem set to help you with the exam. Okay, so that's the driving force. Like our pressure gradient or our concentration gradient, basically this is the push or the pull that an ion experiences in an electrical field. So think about that. The push or the pull that an ion experiences in an electrical field. So, do you remember when I was talking about Einstein's relation, how he actually saw diffusion like little hopping fleas? Well, it was Andrew Huxley that actually said electrodiffusion is like hopping fleas in the wind, right? The wind is the driving force. It's pushing those hopping little fleas. It's the push or the pull that an ion experiences in an electrical field. Okay, pretty good? Stop me if you have any questions. Question? I am. Yes, thank you for asking, actually. I have forgotten, and then I kick myself. I go back to my office. I'm really sad, so thank you for asking. All right, so yes, this is the driving force, push or pull that an ion experiences in an electrical field. All right, so resistance. Our garden hose physiology analogy was the kinking of that hose. It's the same thing here. The resistance is the difficulty with which an ion moves across the membrane. So perhaps a channel is closed, an ion channel is closed, or there's not many channels in the membrane, and it's very difficult for an ion to move across the membrane. We would say that the membrane would have a very high resistance. It's the difficulty with which ions move across the membrane. Conductance is just the inverse. So conductance usually it's depicted as a small letter G. It has units of Siemens. I forgot to say that resistance actually has units of ohms. And conductance is the inverse of resistance. You can actually see the equation down here at the very bottom of the slide. Conductance, depicted by the G, is equal to 1 over R. It's the inverse of resistance. You can calculate that. It's the ease at which ions move across the membrane. If it's very easy for ions to move across the membrane, we say it has a very high conductance or low resistance. Does that make sense to everyone? All right, so these terms are important. A lot of times, even a year later, I understand that, sometimes these don't stick with you, but students still ask, voltage, current, resistance, conductance, all still a little fuzzy. But I really want you to commit this to memory because this is really important stuff relating to physiology, okay? So understand these terms, and again, the type of questions you'll see on the exam is really just terminology. Okay, you might see This is the push or pull that an ion experiences in an electrical field. Is that A, current, B, driving force, C, resistance, D, conductance, okay? So those are the type of questions that you'll see on the exam, okay? All right, so again, let's move on to, I'll go back to this slide because we're going to use it in just a second. We're going to run some numbers, especially when we get to the chord conductance equation. But I want to go back to the syllabus, right? I want to talk about Ohm's law again. Remember, this is Ohm's law from 3 different perspectives, either from using chemical terms, hydraulic terms like our garden hose physiology, or now we're concentrating on the electrical terms, okay? So, transport units, the flow is current in coulombs per second. Driving force is the voltage gradient, or the potential difference, okay? That's the driving force. Resistance can be resistivity or conductivity, just remember they're the inverse, or the diameter of the conductor. The larger the diameter, the greater the conductor. Okay. All right, so hopefully Ohm's law is fairly clear right now. Let's move on. Let's talk about the resting membrane potential. Okay, covered Ohm's law. That's pretty much all that I want you to know about Ohm's law for now. The resting membrane potential. All right. So this is essentially the membrane potential that you would measure with a voltmeter. Remember, you just impale the cell and you can measure that inner leaflet compared to the bath. We're going to revisit Bernstein's hypothesis and explain how the resting membrane potential is generated and measured. Understand the differences between equilibrium and steady state. And know the meaning of the constant field equation and the chord conductance equation. Okay, so let's start with the resting membrane potential. All right, you've seen this particular slide already. I just want to review to make sure that you know the difference between the equilibrium potential and the resting membrane potential. You really have to know the difference between the two. Again, this is the type of question that will be on the exam. The equilibrium potential, you can calculate the exact voltage where you would be at electrochemical equilibrium by using the Nernst equation and calculating the equilibrium potential. At that exact voltage, that's basically where you're going to prevent the net movement of any ion down its concentration gradient. And at that exact voltage, like a teeter-totter, this is where the electrical work and the chemical work actually equal each other. They're equal in magnitude, but opposite in direction. And in a one-ion system, this was part of our top hat question, if the actual membrane potential that you measure with the voltmeter is equal to the equilibrium potential, then there will be no net movement. Okay, so hopefully that's clear. Let's move on to the resting membrane potential. Remember, this is a steady state condition. Typically, the actual resting membrane potential is never sitting right on top of any equilibrium potential. So if it's not sitting on top of one of those equilibrium potentials, then you know there's net movement. You know there's movement of ions across the membrane. Steady state is where the influx equals the efflux. Remember my sink analogy when you go into those newer homes and you actually see the sink? If you turn the water on just right, if the water going into the sink, it exactly balances and equals the efflux going down the drain, the efflux of water going down the drain, then that water line will stay steady. Doesn't fluctuate wildly, the resting membrane potential stays steady at -70. So I know this is review, but I just want to make sure that we're really clear on the difference between these two terms, okay? So Bernstein didn't completely explain the ionic basis of the resting membrane potential. in that he assumed potassium was right at the equilibrium potential. What he didn't realize is that there was actually other ions moving across the membrane that was pulling the resting membrane potential away from the equilibrium potential. But he did capture the essence, right? Most of the conductance for potassium, or for the total conductance of all the ions moving across the membrane, most of it is due to potassium, 90%. So he did capture the essence. In most cases, again, the resting membrane potential does not equal the equilibrium potential. And just remember, the resting membrane potential is at steady state. So the amount of potassium efflux that occurs is balanced by an equal amount of sodium influx. All right, so let's start off first with the constant field equation, or the Goldman-Hodgkin-Katz equation. Now, I know I've sat in a lot of physiology courses. A lot of times they throw this at you. Here's the Goldman-Hodgkin-Katz. You can read about it in your textbook. But I want to make sure that you really understand the power, why you're learning this, okay? So take a look at this. This is a way to actually predict the membrane voltage that you would otherwise measure with a voltmeter, okay? If you know the permeabilities, okay, so it's actually very hard to measure permeability in the laboratory. And there is a distinction between permeability and conductance, okay? It's a very slight one, but you can dissect it out experimentally. Okay, so get this. If conductance is the ease at which ions move across the membrane, permeability is the ease at which it enters into the pore. There's a slight distinction. You actually can dissect the two out experimentally. But a lot of people use this term synonymously, but they're not the same. But they basically are very, very similar. So permeability is the ease at which a molecule enters into the pore. Conductance is the ease at which an ion moves across the membrane. So again, it's very difficult to measure permeability. That's why we're going to be using the chord conductance equation in just a second. So just know that every single ion moving across the membrane, every single one, plays a role in setting the membrane voltage. So we've cut off a lot of other ions moving across the membrane. We've kind of just distilled it down to three major ones. We're assuming that only potassium, only sodium, and only chloride are moving across the membrane. And all three of them are playing a role in setting the membrane voltage. All right, now let's just pretend that we blocked sodium and we blocked chloride. So now sodium and chloride are essentially zero, right? The permeability for both are zero. What does this equation look like to you now? What equation does this look like now? What do you think?
It's almost exactly like the equilibrium potential.
That's right. It's exactly like the equation I gave you to calculate equilibrium potential. It's called the Nernst equation. It is exactly the Nernst equation. All right, so what that means is if only one ion is moving across the membrane, then the equilibrium potential is the resting membrane potential. Does that make sense? If there's only one ion moving across the membrane, then the equilibrium potential is the resting membrane potential. Okay? So again, Bernstein had it almost right. He just didn't realize that there was one other major ion moving across the membrane, which was sodium. All right. So because permeability is actually very difficult to measure in the laboratory, and this equation can be kind of clunky, I'm going to roll out the chord conductance equation, which also allows you to predict membrane voltage. It's just a little bit easier to use. All right, just another equation to predict the membrane potential. The actual membrane potential you would measure with a voltmeter. So again, experimentally, it's easier to measure the conductance rather than the absolute permeability. So the equation that's often used to calculate resting membrane potential is called the chord conductance equation. Okay? All right. So with this, let's play a few mind games here. Brain teasers, right? If you will. Brain teasers. All right. So I'm just going to give you a couple of equilibrium potentials, okay? You know how to calculate equilibrium potentials now, all right? All right, so let's just say we already calculated the equilibrium potential for sodium. And we calculated it to be plus 61 millivolts. Okay? Here's 0 millivolts. And here is the equilibrium potential for potassium. And we're going to say minus 62 millivolts. Okay? Now, normally, and I will give you this on the exam, when you look at the total conductance, and I'm going to use GT, that's the total conductance. Typically with a cell at rest, when you look at the total conductance, 90% of the total conductance is due to potassium. 10% is due to sodium. So we could write this equation. The conductance, the relative conductance is 0.9 for potassium. And if we add that together with sodium, it would have to equal 1, right? Okay, so going back to the chord conductance equation, let's just show, I'm going to show you this right here. Here is the actual chord conductance equation. And again, you don't need to memorize this. This is in a 2-ion system. Only sodium and potassium are moving across the membrane. So the total conductance is equal to the conductance for sodium plus the conductance for potassium. All right, so here's the chord conductance equation. The membrane voltage is equal to the relative conductance of sodium over the total conductance. This would be 10% or 0.1. Multiply that by the equilibrium potential for sodium plus the conductance for potassium over the total conductance. This is 90%. So this would be 0.9 times the equilibrium potential for potassium. So I'm going to let you, I'll write this equation and I'll let you solve. Here's our equilibrium potentials. You can predict the membrane potential by using the conductance for sodium over the total conductance times the equilibrium potential for sodium plus the conductance for potassium over the total conductance times the equilibrium potential for potassium. All right, so I'll let you calculate that out. You can see the equilibrium potentials. Conductance is the ease at which ions move across the membrane. So most of the pathways for allowing ions to move across the membrane is stated right there. 90% of the total conductance is due to potassium leaving the cell. Only 10% is due to sodium. So how would you set this up? And where would you predict the actual resting membrane voltage to be? The actual resting membrane potential, where is it sitting? When you have the answer, just raise your hand. Let me know. Yeah. 5.2 millivolts. I think you're close. I think that there's one piece missing. So what you want to do is you want to say 0.1 times plus 61 millivolts plus 0.9 times minus 62 millivolts. So I think I have an idea of where it should be. You might be one decimal off, actually. Did you say minus 5? Yeah. So let's keep working it. Let's keep working that. Let me just... Okay, so what I am getting here, let's do this together. 0.1, 0.1 times 61 is what? 6.1. Okay, so that's the first part. 6.1 millivolts. And then what's this one at the 0.9? Yeah, negative 55.8 millivolts. So now when you add 6.1 plus minus 55.8, what do you get? That's right. Negative 49.7 millivolts. I thought it would be about 50, right? Okay, so that's going to be right here, right? Minus 49.7 millivolts is the resting membrane potential. Notice that I did put it as a solid line because if you did actually measure it with a voltmeter, it would be about that. All right, so just take a moment to think about this. If you actually look at this graph without even doing any calculations, you could almost predict that this is 1/10 and this is 9/10. 9/10, right? So this, when basically you have a larger conductance, it tends to pull the membrane voltage closer to the equilibrium potential. So it's very close to the equilibrium potential for potassium, right? Because the conductance is so high. If it was all due to potassium, then the resting membrane potential would be actually sitting right on top of the equilibrium potential for potassium. So without doing any calculations, let me just ask you a question. What if the relative conductances were 50-50? Don't even do a calculation now. Where would the actual resting membrane potential sit? If the total conductance was 50% due to sodium and 50% due to potassium, where would the actual membrane voltage sit? Right around zero, exactly. It would actually, now that there's a larger conductance for sodium, it would pull the resting membrane potential very close to zero. It'd be like right in between the two equilibrium potentials, right around zero. Okay? Let's just play one more game. What if 100% of the total conductance was due to sodium? Where would the actual resting membrane potential sit? 61. It'd be sitting right on top of the equilibrium potential for sodium. Now here's where we're going with action potentials. Okay? The resting membrane potential sits right here, about 9/10 of the way, very close to the equilibrium potential for potassium, because there's these leak potassium channels in the membrane. It's setting the resting membrane potential. Now imagine in your mind all of a sudden these voltage-gated sodium channels open, right? voltage-gated sodium channels open. Now the relative conductances are 90% sodium, 10% potassium. Isn't that going to pull the membrane voltage closer to the equilibrium potential? Right? About 9/10 of the way, so I'm going to stop right here. Then the sodium channels close, and an additional potassium channel population opens. That pulls the membrane voltage back down, even closer to the equilibrium potential for potassium. And then that second set of potassium channels close, and it goes back to rest. Doesn't that look like an action potential? Now that you know the chord conductance equation, isn't that cool? Now you understand the ionic basis of the action potential waveform. I'm going to add on one more. It's not about concentration changes. Do you remember the computer simulation? It's not about changes in concentration or the concentration gradient. It's all about just opening and closing channels that give you sweeping changes in membrane voltage. The concentrations don't change like that computer simulation. This is the ionic basis of the action potential waveform. This is where we're going. Okay, it's just about opening and closing channels, changing those relative conductances, moving that membrane potential. This is the signal, the electrical signal that propagates down an axon. All right, so that's all I really wanted to really hit home today. What I'm going to do is this is going to be kind of a workshop now. If you really understand it, you're free to go. If you want to stay and really hammer out some of these concepts, I will stay. And we will work on the board, the whiteboard, until you actually really solidify this in your mind. You should be able to, I guess the major thing here is you should be able to do both part 1 and part 2. I haven't passed out part 2, so you'll have to print that out on your own. But they're both due on Wednesday, and you should be able to do the entire sheets. Okay? All right, you had a question. Oh yeah, you'll have to. Yeah. You'll have to print that one out. All right.
So you're saying that so when it's just one ion, the equilibrium potential will equal the resting membrane potential?
Yes, the resting membrane potential will equal the equilibrium.
So it's confusing, one of the problems that's when we have just one ion we're focusing on, and they give us the resting membrane potential is 70 or something.
Yeah, I just gave that to you, so you can assume there's other ions.
Okay.
You can make that assumption.
Okay, gotcha.
Yeah.
So it's not.
Sure.
Okay.
Yes. Or did you just want to take my name and give it back?
I just needed to take your name.
If that's easier for you. Alright, just give me 1 second.
I'm just lost.
Oh, wait.
What am I supposed to do today? It's 30. Alright. No, it's just
All right.